Lecture 7 and its worksheet. In this lecture, we will learn about the measures of position in a data set, and these are mainly z-scores, percentiles, deciles, and quartiles. And we will learn how to give a summary of the data by using 5-number summary, and how to visualize it by using the box plot. And also we will look at the relation between the box plot and the skewness of the distributions. Skewness of the distribution of the data. Measure of position is a way of explaining where a particular data value lies on a given set. So it's basically telling what position, what's the position of the data inside the data set. So we have 4 measures of position, like we have z-score, the percentile, decile, and the quartile. Z-score. So z-score is it shows the position of an x value in the data set in a certain way. So it's a measure of position, and the z-score calculates how far a data value x is from the mean in terms of standard deviation. So if you write it in the as a formula, the z-score of a value of x is equal to the x value minus the mean of the data divided by the standard deviation of the data. And we have the z-score of a data value as here x minus mu divided by sigma if the data set shows the population, and if data set is taken from the sample. We have the same formula with the symbols for the sample, so x bar and s we use for the sample mean and the standard deviation. Now, one other thing is, if the z-score of a data value is 0, then the data value is same as the mean. So it is easy to see here. If x minus mu divided by sigma is equal to 0, so this is the z-score of x. You can say it's x equal to mu here. The data you took, x, is equal to the mean. And in the same way, if it is bigger than 0, you will get x is bigger than mu. And if you take less than 0, so you will get less than mu. So these sentences are telling these situations. If the z-score of a data is bigger than 0, this data value is above the mean. If the z-score of a data value is less than 0, this data is below the mean. Okay, now let's see how we use z-scores in practice. Assume we are given 2 data values from 2 different data sets, and then we can compare the positions of these 2 values in their own data sets with z-scores. So let's see this in an example. A student scored 65 on a math test that has a mean of 50 and a standard deviation of 10. And she scored 30 on a statistic test with a mean of 25 and a standard deviation of 5. So compare her relative positions on the 2 tests. So student score, math score, okay, I will just say math score of the student is 65. And then the mean of the math scores is 50. And then the standard deviation of the math scores are just 5, no, 10. Now, this is student's math score. This is the x value here. It's the x value. This is one of the data, one of the scores among the math scores. And now for the statistic, we have this information. Student's stat score is just 30, and the mean of the statistic scores is 25, and the standard deviation of the statistic scores is just 5. So we have 2 data sets, and we have 2 scores to data values. We want to see their positions in the data set. So we are finding the z-score of 65 in this data set. So we should do 65 minus the mean, 50 divided by the standard deviation, which is 10, and it gives us 1.5. And now when we look at the z-score of the student statistics score, which is 30, minus 25 over 5. Now, z-score of 65 in mathematics is 1.5, and the student's z-score of the student score is just 1 here. When you calculate, this is 1. So when you compare here the positions here, 1.5 is bigger than 1. So you can say here the student's position in math is better than his position or her position in statistics. Now let's see. Okay, I will remove all the typing here. So we say at the end the student has a relative position in math test because the z-score of math is bigger than the z-score in statistic. So here is what you can do here. The quartiles divide an ordered data set into 4 equal parts. We can call these parts quarters anyway. So let me give you a concrete example here. 1, 2, 2, 4, 5, 6, 7, 7. Okay, we have 8 numbers here. Let's say 8 numbers. And if you want to divide it into 4 equal parts, you have to divide them like half into half first. Okay, you divide from here, and then the other parts, the second half and the first half, divide again. So in this case, these are the separators, or we say the quartiles. And here, how you find this one? This is the median of the first half. And how can you find this one? Like 2 plus 2 over 2, the median of this part. And this is the median of the whole data, And we call this one Q2, the second quartile. And this becomes just, you know how to find this, like 4 plus 5 divided by 2. This is 4.5. And the median of the second half is called the third quartile, the median of the third quartile, the median of the second half, we call it Q3. And you can find them. I mean, we will see them in the examples. And let's talk about how many percent of the values fall below the quartiles. Now, let me give you a scale here. So here, Q1, we have 25% of the data falls behind Q1, and 50% of the data falls behind Q2, equal or less, okay? And 75% of the data falls behind Q3, or it might be equal to Q3. So let's see the example. So in this example, we will find the quartiles, the first quartile, second, and the third quartile of the following data. The first thing you have to check is the order of the data. Is it in ascending order? So as you see here, 5, 6, 2, and 4. So as you see, it's not in ascending order. If it is not in ascending order, first we have to arrange the data in ascending order. So you can do like 2, then 4, then another 4, 5, and then another 5, then 6, then we see 6, and then this 8, and we have 9. Okay, then now in order, now in ascending order, we did it. Now the first thing you have to do is first find Q2. So Q2 is the median of the data. Now, what is the median of the data? How many values are we at? Do we have 1, 2, 3, 4, 5, 6, 7, 8, 9? So 9 numbers. How can we find the median here? The shortcut is 9 over 4. It's 4.5. So the fifth one is the median. The median is the fifth one. So you can say here 1, 2, 3, 4, 5. Here 5 is the median. So it divides the data into two parts, as you see. Now find then find Q2. Find Q1. Sorry, Q1 is now the median of the first half. So what we mean here is this. So how can you find the median of 2, 4, 4, 5? So it's basically you just find the middle numbers because we have an even number of numbers. So we have 4 and 4, and you add them, divide by 2. If you don't remember how to find the median of such thing, please check out the median slides. And we got Q1 here. And we do the same thing for the second part, and it corresponds to Q3. So Q3 is okay, the mean of the second half, I will say. And what's the mean of the second half? We have 4 numbers here, and we look at, okay, since there are 4, so we look at this two middle numbers. So we add their, okay, we add them and divide by 2, so it becomes 7. So Q1 turns out to be 4, and then Q2 turns out to be 5, and Q3 turns out to be 7 in this data. The interquartile range of a data set is the difference between Q3 and Q1. We can write it as like IQR is equal to Q3 minus Q1. And where do we use it? We will use it in finding outliers. Okay, we will see it later in coming slides. Okay, let's look at this question. It says find Q1, Q2, Q3, and IQR for the following data set. And the first thing you have to do is you have to order it. So be careful here. This is very important. It's not in order, so you have to arrange them in an ascending order. So arrange the data in order from the smallest to the highest. So as you see now, it's arranged in order. So then you can find the mean. So 1, 2, 3, 4, 5, 6, 7, 8. So if it is 8, so where's the mean here? The mean will be here. It's 4 here and 4 here. So the mean will be, sorry, the median will be, so this Q2, it becomes the median here. So the median is 24 plus 26 divided by 2. So it is 25. And then after we find the second quartile, so we have to look at the first half. When you look at the first half of the data set, the median here, the median of this part becomes Q1. And as you see here, the median is equal to the average of the middle terms, which are 20 and 21. So it becomes 20.5. Now, when it comes to the other one here, the right part, as right half, so the median is, it should be here so that it divides the data into two sets. So then Q3, it will be 27 plus 30 divided by 2. So this is the median of the right part, right half. Okay, let's see them in. Okay, this is how we find them, and these are the values we get. Let's see, it's 25, 28.5. And what can you say about the IQR? IQR is just Q3 minus Q1, so it will be equal to 8. Deciles are the values that divides the data set into 10 groups of the same size. They're like quartiles, but we divide the data into 10 groups. So we have 9 deciles, and each decile here is leaving the 10% of the data behind. So D2 leaves 20% of the data behind, and D3 leaves 30% of the data behind. So it goes like this. You basically divide the data in 10 groups, and these separators are the deciles. Now here, the first decile of a data set is the smallest value, D1, we call it D1, for which at least 10% of the data are less than or equal to D1, as I said here. Now, the ninth decile of the data set is the smallest value for which at least 90% of the data are less than or equal to this data set. And the interval from D1 to D9 is called the inner decile interval. And interdecile range, so here I think this is interdecile interval, and interdecile range is the difference between D9 and D1. So you can write here as D9 minus D1. And now this is important. So how can you find the value corresponding to the decile dm? So you want to find the decile, the empty decile in a data set. So how can you find it? So you arrange the data set in ascending order and assume you have n numbers. You have n numbers in a data set, and then you will calculate C value. So what is C? C is basically n times m over 10. What is n? It's the number of the values. What is m? You are trying to find dm, so the empty decile. So you're trying to find the empty decile for n numbers. Then you find C, and here is the rule, depending on C. If C is a whole number, you got C here, and if it's a whole number, then the empty decile of this data set is C plus one number and C plus number divided by 2. And if C is not a whole number, you round it up to the next whole number, and let's say it's K, then you say the M is the K number in the list. So let's do the example here. What is D1 and D9 for the following data set? Here, the first thing you have to do is you have to write it in order. So arrange the data in order. Now, you want to find, let's say, D1. Okay, you want to find D1 decile, the first decile. So how many numbers are there? N is what? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 values. What is M here? You are trying to find the first decile. You write here M is equal to 1. Then you find C. 9 times 1 divided by 10. So it will be 0.9. And then this is not a whole number. Then you round it up. To a whole number, so you get the 1 when you round it up, and then now you say the 1 is the first number. The first is coming from here. So this will be first number, and it will be D1 will be the first number in the list. And here it's just 2. Now we can do the same thing here for D9. So for D9, okay, I will erase here, I will erase this part, and I will erase this part, and I will erase this part here. So let's do it for the 9. So M becomes 9. So we have 9 times 9, this is 8.1, so this becomes the 9 here when you round it up. So this will be just 9th number. So 9th number is here 9 when you count. So the 9 will be equal to 9. If you want to calculate another one, you do the same thing, as long as you find N and M, and then you find C, and it's not a whole number, you round it up, and then you find the decile. Now choose the correct answer. A student scored 54 on a philosophy test with mean of 51 and a variance of 25. And find the z-score of the student, or z-score of 54. So as you remember, z-score can be calculated by the value, the x value. So this is the value we got here. We want to find the z-score of 54. 54 minus the mean is 51 divided by the standard deviation here. The standard deviation is not given in the question, so it's not given in the question. But can we find it? Yes, the variance is given. So we know the variance is 25, and we know the standard deviation is always the square root of the variance, and the standard deviation has to be equal to the square root of 25, which is 5. So then it will be 5 here now. So when you do this calculation, you'll end up 3 over 5, which is 0.6. So this is 0.6. Now find the first quartile, the median, and third quartile for this data set. Now the first thing you have to do is order the data. And let's say 1, and then 2.5. Sorry, this is 1.5, then 2.5, sorry. And then 3, and then 5, 8.5. So how many? 1, 2, 3, 4, 5, 6, 7. And here 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Okay, good. So then we find the median here. So we have 7 numbers. So in 7 numbers, we will have 3 and 3, and then here 1. So because we have to divide into 2 equal parts, so it will be 3 numbers here and 3 numbers here. So this becomes the median. So median is called the second quartile also. It's 3. And now the median of this part is called Q1, and which is the middle term here, 1.5, because we have odd number of numbers. And now we have Q3 as the median of this part, which is just the middle term here is 8. So we have the answer as 8. Now in the distribution we have Q1 3, Q2 15, and then Q3 42. What is IQR? IQR is, remember, it's Q3 minus Q1, so this will be equal to 42 minus 39, which is sorry, this is Q1, this is 3, so this has to be 39, then this is the answer. So let's look at the percentiles now. The percentiles divide the data set into 100 equal groups, and these are divided by, and these are denoted by P sub 1, P sub 2, P sub 3, and P sub 99. Now, in some exams, they use it, the percentile, because they say you are in the 19th percentile. So if you're in the 19th percentile of your class or your scores, the math scores, so it means that your score is higher than 90% of the class and 10% lower than the 10% of the class. So um, okay, how can we find the percentile corresponding to a given value? So assume a data value, we pick the data value from the data, and then we ask which percentile is X in. So first you arrange the data. So in the position always, you always a fixed thing. You always arrange the data in ascending order. And then you use the following formula. So the percentile of X is equal to the number of values below X or less than X, and then plus 0.5 divided by the total number of values times 100%. So, or times 100. Let's use, okay, let's look at this example. Consider the scores of 10 students arranged in ascending order. So this is in ascending order, that's good. So it says find a percentile rank of score 14. If you remember it, so where is 14? It's here. Okay, it's arranged, data arranged in ascending order. So if you remember the formula is the percentile of X is the number of values below X. Here it's 14. So how many numbers? 1, 2, 3, 4, 5, 6. 6 numbers. So this 6 numbers, you write it here, then add 0.5. Then find the total number of values. We have 10 values here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that will be 6.5 divided by 10 times 100. So it will be 56 percentile. So 14 is bigger. I mean, 14 is in the 65 percentile. So it means it's more than the 65% of the data. Or you can say the student whose score is 14 did better than 65% of the class. Okay, now let's see how to find the value corresponding to a given percentile. And first, arrange the data set in ascending order. And then to compute the mth percentile or P sub n, find C, and here C can be calculated by n times m divided by 100. So n is the number of the values in the data set, and then m is coming from the percentile. And then if C is a whole number, then the mth percentile is the seed number plus C plus 1 number in the list divided by 2. And then if C is not a whole number, then we will round it up to the next whole number, let's say K. The rounded number now is K. And then PM or mth percentile is the kth number in the list. Now let's look at this example. Find the values corresponding to the 25th percentile and 70th percentile given the following data set. Now the first thing you have to do is you have to arrange the data in ascending order. Now the value is already, I mean the data set is already in order. So you need to, okay, you have to find C. So n is here, n is the number of the values here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so n is 10. And we're looking for the 20th percentile, so m will be equal to 25. Then we use these values to find C. And when we get, okay, we get C as 2.5, and then we round it up to the next number, the whole number, it's 3. So then we say 25th percentile is the third number in the list. So what's the third number here? 1, 2, 3. So it becomes 7. So 25th percentile is 7 then. Now let's do the same thing. Now again, N is 10 and M is 70 here. Then we find C, so we put these values here, 7. And as you see, this is a whole number. And if it's a whole number, then this will be 70th percentile will be 7th number plus 8th number divided by 2. So you check here 1, 2, 3, 4, 5, 6, 7, and 8. Your 8 and 7th numbers are 14 and 17. We add them, divide by 2, and we get 15.5. So the 70th percentile is equal to 15.5. Now let's see how let's the comparison between the quartiles, deciles, and percentiles. Now this is dividing the quartiles or dividing the data into quarters. Deciles are dividing the data into 10 groups, and the percentiles are dividing it to 100 groups. So these are the separators. This Q1, the quartile 1, this 25% is the values over here before Q1. And for the deciles, for example, D1 has, 10% of the data is below D1, and 20% of the data is below D2. And when it comes to the percentiles, so like here, for example, 25% of the data is below the 25th percentile. So then we can say here for the 25%, for the 25% data, the separator here is the first quartile or P25. So you can say now P25 and Q1 are same. So then you can do the same thing, like 50% of the values here are less than Q2, and P50 has the same issue here. 50% is here, so you say Q2 and P50 is same. And also we have the same thing for the 5, again 50%. Okay, you can compare them by looking at the percentages. So this gives a idea. Here this is 50% is below Q2, and here 50% is below the 5, and then 50% here is below P50. So you can say all they are same. So you can write here P50 is equal to D5, which is equal to Q2. And you can also look at here the 75% here, and it corresponds to, again, here 75%. So you can say Q3 is equal to P5. Here, when you do the 75%, it comes somewhere here, but there is no decile corresponding to this, so we don't take a decile here. So you can say here Q3 is equal to P75. So you can do this comparison this way. So and here for sure this D1 will be equal to P10, because we have 10% here. It will be just P10. D2 will correspond to P20 for sure. You can rate them, you can compare them this way, but these are the main here separators of the data. And here let's look at the outliers. So an outlier is a data point or data value that is an extremely high or low data value when compared with the rest of the data values. For example, let's look at here. We have a data set. It goes like 1, 15, 16, 20, 22, 25, 26, and 100. So look at here. 1 is the smallest value, and there's a big jump after 1. And then these values are relatively close to each other, you know. But here there's a big jump here from the 26 to 100. So these values, the very small values, or the values very far from the other values, are called outliers. So how can we decide, how can we determine the outliers? Um, Here is the criteria we use. If a data value is less than Q1 minus 1.5 IQR, or greater than Q3, the third quartile plus 1.5 IQR, then this data is an outlier. Okay, let's um, look at the steps to identify outliers. Arrange the data set in ascending order, and then find Q3 and Q1, and then find the interquartile range, the Q3 minus Q1, and then find W1. Okay, we call it W1, so you basically find this value here, the first quartile minus 1.5 times IQR, and then quarter 3 plus 1.5 IQR, and then it makes W1, W2, and here choose the values, or the value in the data set that is or are smaller than W1 or larger than W2. These are the outliers. And also it is possible to not have um, outliers. You don't have to have an outlier in a data set. Sometimes when you apply the criteria, sometimes you don't get any outlier. It is possible. Now let's look at this example. Find the data. The following data set gives the prices of a sample of 12 textbooks randomly selected from a university bookstore. And here is the list of the prices. Now find if there is an outlier in this data. The first thing you have to do is, it has to be in order. So you have to put them in ascending order, then find Q1 and Q2. If you remember Q1 and Q2, how to find them, you just find the median here, the median. So you have 12 numbers. So it will be 6, 6, 1, 2, 3, 4, 5, 6. So this will be 6. The first half and the second half, there will be 6. Okay, I made a mistake there. 6 is 1, 2, 3, 4, 5, 6. Okay, then here are the other 6s here. So then the first half is these 6 values. Then their median here, it makes 3, 3. So how can I get the median? The median is the separator of the data. So it will be Q1 will be 93 plus 12 divided by 2. And Q3 will be the separator of the second half. So it's here. So 132 the third quartile. This will be 132 plus 161 divided by 2. Okay, after this, we can find the interquartile range. Okay, let's see the result. Now Q1 equal to 102.5 and Q3 is 146.5. Then we need to find the quartile, the interquartile range. The interquartile range turns out to be 44. And then we have W1 as Q1 minus 1.5 times IQR. And if you substitute these values, in the formula you will get 36.5, and here W2 Q3 plus 1.5 times IQR equal to 146.5 minus 1.5 times 44, which is 212.5. Now we check if so we check here the data or no, let's do it here. So because it has to be arranged, it's already arranged, but you do it in the arranged data. Check if there is a value less than 6.5. Okay, look at here, no, or bigger than 212.5. Yeah, here check no. So in this case, you write there is no outlier because there are no numbers less than 36.5 and bigger or bigger than 212.5. Now let's look at the 5-number summary and the box plots, and they're related to each other. So if you find the 5-number summary, then you make the box plot. Now, a 5-number summary of a data consists of 5 statistics of the data. This minimum and the quartile, the first quartile, the second quartile, or the median, the third quartile, and the maximum. These 5 values of the data we call them the 5-number summary of the data. Now, by using them, we can make a box plot, and the box plot is something like this. So you put the minimum value and the maximum value, and you put all the Q1 here, then Q2 here, and then Q3 here. Now you draw a line and place all this minimum, the first quartile. So that you mean 5 numbers here. Put the 5-number summary on a line. And then from Q1 to Q3, make a box, and then draw Q2, divide the box into 2 from the Q2. So this is called a box plot. Now here, sometimes this is called the box and whisker diagram. So the whisker is, the cats have whiskers, here this parts are called the whiskers. Now we have the cats. So these are the whiskers here. Anyway, we have box and whiskers diagram also, it's called. And you should be able to tell from the box plot and what is Q1, Q2, and Q3, and the minimum and the maximum. Sometimes instead of giving Q2, Q3, Q1, we give you the box plot, and you should be able to tell these values, or vice versa, the other way. Now, these are the steps for the box to construct a box plot. 5 numbers. First, you have to find the 5 numbers. 5 numbers here: the lowest value, Q1, median, Q3, and highest value of the data, and draw a line, horizontal line at a convenient scale. So there has to be a certain scale here. You cannot do like 1 here, 2 here, then 3 here. No, it has to be a good scale here. So you have to do it properly. 1, 2, 3, 4. Okay. Now draw a box above the line that extends Q1 to Q3. Draw a line segment inside the box. Okay. Now you will see this. You will see them questions in the examples. Now look at the example 8. The temperatures in Saudi Arabia for the last 7 months were 23, 25, 21, 28, 30, 22, 31. And it says construct a box plot for the data. So you need to write the 5 numbers summary first. So in order to do it, first you arrange the data. Now this is arranged. So you see this is not arranged. So arrange the data in ascending order. Then find, okay, for the 5 summary we need Q2, we need Q1 and Q3, and the minimum and maximum. Let me remind you how to get the median. We have 7 values, so there will be 3 of them here and 3 of them here. So we have a middle value. This becomes the median or the second quartile. And for this part, we have a median here. This makes Q1. And for the other part here, we have the median, which is also called 30. Third quartile, so which is 30. Now you find the minimum. The minimum is 21, and maximum is 31. And we found them, and then okay, we write them explicitly. Now let's try to make the box plot. So we draw a line, and we put the numbers, we place the numbers on the line. So let's start from the minimum, this 21, and then 22, and then 25, and then 30 and 31. Okay, so they have to be in a regular scale. Okay, so 23, 24, so 25, 26, 27, 28, 29, 30, 31. So you see everything is regular position, and the scale is a true scale, or a good scale. And then okay, you choose 25, you choose Q1 and Q2. So Q1, Q2. Okay, I will raise my scale here. So then Q1 corresponds to 22, then Q2 is here, sorry, this is Q3. And then this is your box plot. So these are called here, the lines are whiskers. And this is the box. Sometimes this is called the box plot or box and whiskers method or plot. Now I want to talk about the box plots and the skewness, but before this one I want to remind you about the skewness of the distributions. So if you remember, we have a raw data, and then from the raw data we make a frequency table, and here we have these values here, we have the frequencies here, and then from here we make a histogram. Here we have this one, I mean, it might be a graph like this, a histogram like this. And if you remember, if our graph, okay, we don't, we don't use the bars here in general. We say the graph looks like this. We say we use curves. So if your data is something like this, then it's right skewed. We say, and okay. And then here, if it goes this way, so we say this is left skipped data, or the distribution is left skipped. And if we have this case here, so we say this type of thing is like, we call it symmetric data or symmetric distribution, or bell-shaped, let's say. Bell-shaped. So there are 3 types of skewness we have seen. Oh, the data doesn't have to be this way, but most general types are the right skewed, left skewed, and symmetric. Now, then we can start the box plots. Now we will look at the relation between the box plot and the skewness of the data. Now the box plot can give an idea about the skewness of the distribution of a data set. Now let's start the symmetric and bell-shaped distributions. So what okay, what kind of box plot? The question is what kind of box plot gives a symmetric or bell-shaped distribution? Now, assume you are given a box plot, and here I will say this is okay. So you will have such graph, such box plot. Assume you have this one. Now here in this box plot, okay, I will make it clear. I will say this is the right line. I mean left line. Sorry, left whisker or left line. This is the right line. And I will say this is left box. This is right box. Now, okay, from now on, keep them in your mind: the left line, left box, right box, and right line. So for, okay, what kind of box plot gives a symmetric distribution? So the idea is this: if you have a such box plot, you will have a symmetric graph of this data. So what's the criteria in terms of the line in the box? So the right box will be equal to the left box. And the right line is equal to the left line. So what we mean here is in length. They have to be the same in length. Now, let's see a positively skewed data and its plot, its box plot. This is not this type only. There are different types. I mean, there are different box plots, but the typical behavior is if you have a box plot in this line, this part is bigger here, and we will have a bigger part here. And if this is the box, and we can have a positively skewed data here, this Q1 is here, Q2 is here, and Q3 is here. And let's look at a negatively skewed data in its box plot, and we have a left skewed or negatively skewed data, and its box plot is given. And here this is Q1 and Q2, and this is Q3. And this is, you see it's short, this part is short, and this part is longer. And we will have a negatively skewed data like this. The graph will look like this. Anyway, we will look at the detail here. In the following three cases, we get a positively skewed distribution. Now, so these are given to us, the box plots, and look at this cases here. If right box is bigger than left box, so you see this line, this is bigger than, definitely bigger than the left one. You know, the right box is this one here, right box, and we say right line, and here is, let's say, left box, and here left line. Now, if you have this case, right box is bigger than left box, and right line is bigger than, or the longer than the left line. So this is the case here. The right line and right box, they are longer, both longer. So in this case, we have a positively skewed distribution. Now, if this is the case, the boxes are same length, so they are same. But the lines here, the left line, so right line, so the right line is longer than the left line here, so we have again a positive skewed distribution. And if the the lengths of the lines are same, but the right box is bigger than the longer than the left box, in this case again we say the distribution of data is positively skewed. Now in the following three cases we get a negatively skewed distribution. Now again, look at here. Now in the negatively skewed, or we generally say left skewed distribution, you will see the dominance of left box, left side. Okay, left box if left line, so they are bigger, both bigger. Or if there's an equality, still the left line is bigger than the right line, or the longer. And if you have an equality in the line length, so again in the left box is bigger than right box. So you see a left skewed, so there will be a left dominance in terms of box lengths in the line lengths. So in these cases, in each box plot shows a negatively skewed distribution here. So in these two cases here, the data cannot be determined from the box plot. Now here, look at here, the right box is smaller than the left box, and the right line is bigger than the left line, so there is no dominance of right side. And here, if there is no dominance of the left side either, so then we say this cannot be determined here. Sometimes for these we don't give the box plots. You have to be careful about this, Q1 here, this is Q1, this is Q2, Q3. You have to check the distances when we give the 5-number summary. You should be able to tell from the 5-number summary the skewness of the data. I mean, you don't have to be given the box plot. You might be given just 5 numbers summary and then asked about the skewness. So these are the two cases that we cannot determine the skewness of the distribution. Now let's look at these questions here. Let's do the exercises. Find a percentile rank for the value of 15 in the following data set. You can go back and look at how to find the percentile rank for a value, but let me tell you, this percentile rank for a data value is equal to the number of the values less than 15 . Okay, then you will find this number, and then you add 0.5 and divide it by the number of the all values times 100%. But here, be careful, and the data should be in order. I mean, if you want to do it, and it's already in order, so it's in order, so there is no problem. So the number of the values less than 15, 1, 2, 3, so it will be just 3 plus 0.5 divided by the number of values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be 10 here, so it will be 3.5 over 10 times 100%. This will give you 35%. Which is a part of 5-number summary. So remember the 5-number summary, it was the minimum, then Q1, then Q2, Q sub 3, and then maximum. Now, which one is a part of? Do you see any of them here? We don't see them as in Q notation, but we know that Q2 is, the other name for Q2 is just a median. So median is a part of 5-number summary. Find the value corresponding to the 65th percentile in the following data set. First, you have to check if the data is in order. Yes, it's in order, ascending order. Ascending means like increasing order. That's good. So how can you find P65, the 65th percentile? You have to calculate the C value first. It's just 65 times the number of the values here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. 10 divided by 100, 6.5. So round it up because this is not a whole number. It becomes 7. So round it up. So you round it up and it becomes 7. So P65, then you say it's the 7th number in the list. So 7th number, 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, now it's 17 then. 7th number at 17. Now, according to the box plot shown below, the distribution of the data is called, it is what? Okay, now here, we check the boxes here, check the length of the boxes and check the length of the lines. So here, right box is definitely right box. Okay, right box is definitely longer than the okay, right box is bigger than the left box. Right box, I mean here, right box. And then here, right line is longer than left line. So you see a right dominance here, so it will be right skewed. So if they are both bigger than the left part, so we say it's right skewed. Right skewed means positively skewed. Okay, let's look at the worksheet problems. Which one is an extremely high or extremely low data value when compared with the rest of the data values? Remember this, like if you have some data going like 1, let's say 25, 26, and then 30 and 35, then it jumps to 200. So these very extreme values, extremely high or extremely low values, we call them outlier because they lie they lie outside of the rest of the data, kind of. According to the box plot below, shown below, the distribution of the data is okay, symmetric, skewed, positive, skewed, or cannot be identified. Okay, now it's asking about the skewness. So here we look at the lines here, the whiskers, the lines. So here we see the lines. Right line is longer than the left line. And here the boxes, when we look at the boxes, the left box is bigger than, so it's longer than the right box is less than or shorter than the left box. So in this case, we don't see any dominance of the right or the left. So because right is bigger than here from the left, but in the second one, it's right is less than the left. So there is no dominance of the right or the left. So we say the skewness cannot be identified. A student scored 36 on a statistic test with a mean of 52 and a standard deviation of 4. And she scored 67 on a math test with a mean of 57 and standard deviation of 5. Compare her relative positions on these two tests. Now let's talk about statistics scores. Now her score is 36, and then the mean of the scores is 52, and the standard deviation of the scores is 4. Now for the mathematics part, her score is 67, and the mean here is 57, and standard deviation of the mathematics scores are 5. So if you want to compare her position on statistics in the math, you have to look at the z-scores of z-score of her scores. So it will be 36 minus 52 divided by 4, which is -4. And so her z-score here is 67 minus 57 divided by 2 and divided by 5. Sorry, this will be just 2. So when you compare these two, her stat score is -4, and -4 is less than 2. This is her her math z-score. So this is her stat z-score. So then obviously her position in statistics is definitely lower than her position in mathematics. So in mathematics, her position is better than her position in statistics. Now, which of the following is a measure of position? If you remember the measure of position, measures of position are z-score and quartiles, deciles, and percentiles. Now, do you see one of them here? Yes. So that will be the quartile. So we have seen the measure of central tendency, and we have the other ones. The 5 number used to construct a box plot are the 5 number store summary. So it will be this one now. This is easy: Q1, Q2, Q3. Now let's use the following data set to determine Q1, Q2, and Q3, the quartiles. Now the first thing you have to check is the order. Is it in order? The data set, yes. So in this case, you find the median. So how many numbers do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can divide this data into 2 groups, like 5 here, and then the other 5 is here. So you can directly say from here, you can find the median here. The median of the data set is equal to the second quartile, which is 10 plus 12 over 2. And for the first half data, for the first half of the data, you can find the mean, which is Q1. So Q1 is the median of 2, 5, 7, 9, 10. And you can say this is here, you have, if you divide it into 2, this will be the middle number. So Q1 is 7. And you can do the same thing for the second part. So Q3 is the median of this part here. This part, so it will be just 18. The IQR is the difference between Q3 and Q1, which is 18 minus 7, which is 11. And for the outliers, you have to find W1, which is Q1 minus 1.5 IQR. And for the high outliers, you have to check Q3 plus 1.5 IQR. So Q1, 7 minus 1.5 times 7. And then here is 8 plus 1.5 times 7. So which are -3.5 and 28.5. Now you check here, you check them, you compare them with this data here. Okay, let's raise now. Okay, you check them. Anything lower than 2.5, nothing lower, nothing lower than -3.5. But here, when it comes to this one here for the high outliers, anything bigger than so let's ask this question: anything bigger than 28.5. So this is the question here. Yes, we have 31. Yes, it is 31. So then you say 31 is the outlier here, the only outlier, and it's a high outlier. Now let's solve this problem. It says, for the following data, find the value corresponding to 60th percentile. First you check if it is in the order. It's ordered. Yeah, it's in ascending order. This is nice. So you don't have to do the ordering. So 60th percentile, if you remember, how can you find the 60th percentile? What you do here is you look at the number here. So how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers. So what you do here is see, you find, okay, if you don't remember, you look back, please. Find the corresponding slide. You write 10 times 60. So the 10 is coming from here and 60 is coming from here, divided by 100, because you're dealing with the percentiles. Then this becomes 6. Now the 60th percentile, so I will say p sub 60 is equal to, so this one here, this one is equal to the 6th number plus 7th number divided by 2, because this is a whole number. If you remember, it was if it's a whole number, so we do it this way. 6 number 1, 2, 3, 4, 5, 6, and 7. So we got these two number here, 20 plus 24 divided by 2, which is 22. So the 60th percentile will be equal to the 20. Now Q1 corresponds to what? So remember that Q1, the quartiles are dividing the data into 4 parts. So we say this 25% of the data falls below Q1, and the rest goes like 50%, 75%. But anyway, we're interested in Q1. So in the percentiles, each percentile has leaving some percentage of the data. If it is like the P1, it's leaving 1% of the data. And the question here is which percentile puts 25% of the data back behind. So this is obviously the 25th percentile, and here which corresponds to the first quartile. So we can say the first quartile is equal to the 25th percentile.